Hello, my name is Babak Naderi from Technical University of Berlin. On behalf of my co-author Russ Cutler from Microsoft Cooperation, I would like to present our paper, an open source implementation of the ITUT recommendation P808 with validation. Traditionally, speech quality is assessed using a subjective test in the laboratory environment, according to the ITUT recommendation P800. The idea is to control for all unwanted factors, including environmental noise, listening devices, and factors related to the test participants. Therefore, one can be sure that the observed effect in the test results is because of the differences between the test conditions. As the subjective tests are costly, different objective models have been developed for specific degradations. However, it has been shown that they have a low correlation to listening opinion tests when applied to speech samples corrupted by other distortions rather ones they were designed for. Alternative to the laboratory test would be the crowdsourcing approach. Microstat's crowdsourcing provides access to a large pool of participants. It is faster, it is cheaper, and more scalable compared to the laboratory test. However, participants perform their tasks in own working environment and using own devices. There is also no personal contact between moderator and the test participant, which is probably something good nowadays. ITUT has published a new recommendation P808 on subjective evaluation of speech quality with a crowdsourcing approach. The recommendation provides details on how to perform the crowdsourcing speech quality test and deals with those challenges for the listening-only test. In this paper, we introduce our open source implementation of the ITUT recommendation P808, the extensions we implemented, which can be added to the recommendation, and also results of validity and reproducibility studies we conducted using our toolkit. Comparing to the other available frameworks for performing subjective tests in online environment, our toolkit is the only one based on the ITUT recommendation, with minimum requirements and include hearing and environment tests to check reliability and validity of the ratings we collect. We also conducted the validity and reproducibility tests for our toolkit. Our toolkit is highly automated to avoid operational errors, and we made it open source to provide basic subjective speech quality tests accessible for everyone without huge cost of building a test laboratory. Our implementation is tailored to the Amazon Mechanical Turk, which is the biggest and by far mostly used crowdsourcing platform. Here I briefly explain the procedure of conducting the test using our toolkit. Let's assume you have already prepared your speech dataset which you want to use in the study. This dataset does not differ from a laboratory test. Besides that, you need three other sets, namely training clips, gold clips, and trapping clips. The training clips will be used in the training section, not only to familiarize participants with the scale and the test procedure, but also for anchoring. The training set should cover the entire MOS scale. As in the crowdsourcing test, there is no guarantee that a test participant read the entire dataset. The gold and trapping clips are used for reliability checks. The gold clips are the audio clips which their quality is evident. Therefore, we expect participants give such a score with a small deviation. The trapping clips are audio-based attention checks. The voice in the clip directly asks worker to select a specific rating category to show their attention. In step A, experimenter can create customized trapping clips for their dataset by running the provided script. In step B, the master script should be used to prepare the test. The master script creates the HTML file for the HIT app the inputs as expected by the HIT app, which contains all required URLs, and also creates the configuration file which will be used later in the post-processing. Next step is to create a project in the AMT using the HIT app and publish a badge for that project. AMT will create instances of the project and make them available for crowd workers. When all assignments are finished by crowd workers, you can download the responses in a single file and run the result parser script. It first screens the submissions based on answers to the trapping and gold clips, the environment and hearing tests, variances in the ratings, and other filters. It marks submissions either to be accepted or rejected, and aggregate the reliable votes per file and per test condition. It also calculates basic statistics including the most values, standard deviation, and 95% confidence interval. Last step is to use the utility script and reports generated by the result parser to accept and reject the submissions and assign bonuses to the worker. On the right-hand side, different sections of the HIT app from participant perspective is visualized. We extended the recommended method in the following ways. In the recommendation, a two-step approach is used, in which first participants are qualified and then invited to the test. There have been two different jobs in the crowdsourcing platform. We integrated the qualification in the test as a first section, which only appears once. The qualification section includes the hearing test. If the worker successfully passed the qualification once, then she doesn't need to do that anymore. As a result, the entire test can be finished significantly faster, as a new worker can join without any active participation of the test moderator. The environment test is included in the setup section, and it normally takes as long as the rating section. We set this section to appear periodically to avoid huge overhead on each assignment. We also added the headset detection component using WebRTC. However, the method does not cover all possible cases. In the ITUT recommendation P808, only absolute category rating procedure is specified. In our toolkit, we also added the degradation category ratings and also comparison category ratings test procedures based on the description given in the ITUT recommendation P800. To assess the validity of the subjective ratings collected by our toolkit, we compared them with ratings collected in the standard laboratory test. We use a dataset from the ITUT Supplement 23. It includes 50 degradation conditions and 4 clips per each condition. The laboratory test was conducted according to the ITUT recommendation P800, and results are openly available. They collected 96 votes per test conditions. We conducted the crowdsourcing test using our toolkit and on average collected 260 reliable votes per condition. We used bootstrapping on our collected data and randomly selected 96 votes per condition with replacement and calculated the most values per condition. Then calculate the correlation coefficients and RMSE between the most values from sampled data and the most values from the laboratory test. We repeated this procedure 10 times. On average, we reached a Pearson correlation coefficient of 0.95 and RMSE of 0.237. We also conducted a reproducibility study. For source signals, we used the wideband dataset from the Interspeech Deep Noise Suppression Challenge, which includes 700 clips. We processed them with 4 different models to enhance their quality. Then we used the processed clips, and the source signals in our crowdsourcing test. We repeated our crowdsourcing test 5 times in 5 separate days. On average, in each run, 89 workers participated and we aimed to collect 5 votes per clip. In the bar plot, the most values of each model for each run is visualized. On average, we reached the Pearson correlation coefficient of 0.99 between different runs. To remove the bias between different runs, we calculated the differential MOS for each model given the MOS values for noisy dataset. This bias is well-known aspect of a subjective test and it appears in any test to retest. We calculate the intra-class correlation coefficients using the MOS and DMOS values. The intra-class correlation coefficients shows how strongly each run of the P808 implementation resembles each other. Results show a good reliability when using the MOS values and an excellent reliability when using the DMOS values. We also look at effect of each component on the accuracy of the previous study. Simply we calculate the MOS values using the votes which passed and votes which failed a filter. For some filters, the number of votes failing was too small, so we did not consider them in this evaluation. Results showed that when all filters are used, the toolkit is more consistent in reproducing similar results. Meanwhile, the headset test did not lead to a significant improvement. In conclusion, a speech quality assessment using the P808 toolkit in crowdsourcing shows high validity and reproducibility. The P808 toolkit provides fast, cost-efficient, and a scalable method compared to the laboratory test. The P808 is highly automated, which avoids operational errors and reduces the active working time of the experimenter. We also extended the toolkit to include other test methods, including DCR and CCR. For future work, we aim to work on other test methods like the ITUT recommendation P835 for evaluating speech communication systems that include noise suppression algorithm, and the ITUT recommendation P831 for evaluating acoustic echo cancelers. The toolkit is open source and available for the community in the following link. Thank you for your attention.